What's up everyone? Today I wanted to showcase you a cool trick that you can use to copy geometry across a surface while also taking in account its size. So the necessity for the setup that I'm going to showcase in this tutorial came from my desire to actually to have kind of like a random tiles across a roof surface. So this is a kind of preview for the tutorial that I'm working on next, which is creating a procedural building inside Houdini. And the roofs are actually created uh, the roof surface is actually created from the tiles that are actually scattered across using like a patches. You can see that if we're going to go ahead and visualize, you can see that all of these colors are its own tile types. So I wanted to achieve this kind of a result, and the setup that I'm going to showcase in this tutorial is actually how I am achieving it. And to showcase this one, I have a little bit more of a simpler geometry here. So you can see it's also basically the same thing, and I'm using this to randomly generate these tiles. So let me go ahead and walk through the way that this is actually set up. So first of all, we have our roof surface that we want to copy our tiles across. And then I also go ahead and go through for each one of these primitives and the actual logic for this. And the actual logic is actually inside the roof generator node for me. So all of these custom HDAs that I'm showcasing in this video are actually going to be available for download when I'm actually going to finish my next tutorial, which is a procedural building inside Houdini tutorial. But in this tutorial, I just want to showcase the logic that powers this kind of a random tile copying. So first of all, we are looping over each primitive, and if you have seen my video about the creating procedural roof inside Houdini, you may remember that I actually created a logic that's actually going to flatten out our primitive and align it along the z or x axis or whatever I was using in that tutorial. So that tutorial is actually going to be linked in the description below, because this is kind of like a prerequisite that we need to do before actually creating our roof tiles, because our geometry always has to be aligned across the z-axis. So you can see that without the transforming the geometry back, we have looped over each primitive, and all of our primitives are actually, you can see 24 points. Each one of these are actually now aligned. And what's cool about this, that we can use the same attribute, the transform that this node has created, so that this custom node that we have basically wrapped around the logic from my roof tutorial for the transforming of primitive across the axis, I have wrapped it around inside this dedicated HDA. So this logic is basically the same as I showcased in that tutorial. And what's cool about this, that after that we have our translate that we can use. Go ahead and use it again to transform our geometry back. And our roof is actually going to be generated across on this flat primitive that we can just go ahead and transform it back. So this is a very powerful way to work, because we have basically kind of like a normalized workspace that we know that all of our primitives are across the positive, are aligned across the z-axis, and it's facing the positive x-axis. It's normal. So let's go ahead and go through this actually logic that power these patches. So first of all, it has two inputs. So the first input is actually the primitive that we want to create our roof tiles on, and then also we need our tiles. So in this case, I have also created a simple roof tile generator node that we can basically preview. We can create different types of tiles, and we can also preview them how they would actually overlap each other. So in this case, I just have 3 different tiles that I have go ahead and imported it back into this null node. And the important part about these tiles are actually the attributes that it has. So I have a vector2 attribute, which is the size of these tiles. So the size are basically x and y, basically the width and height of these tiles. So the height in this case are all the same. it's 0.2, but the width is actually from 0.2, 0.15, and 0.25 width. So this attribute is very important. Also, the unique identifier for each one of these tiles are actually a string attribute, and all of these are actually a primitive attribute. So this is actually, its class is also important. So let's go ahead and go to this roof generator, and let's go inside and let's take a look at how it is set up. So first of all, we're going to go ahead and also open up the parameters for this node, because I want to okay, so I have this here. So let's go inside this node. So first of all, we can go ahead and choose which tiles we actually want to copy. Actually, let me show the end result with these parameter types, with these parameters. First, we have to point to our attributes that the node is going to use. So we need our unique identifier for each tile. So this is the tile name, and also the size attribute, which I have set up as a size. And what's cool about this, that this is actually going to showcase only the valid attribute types as for its drop-down menu. And the way that this is actually powered is from the Python menu for these parameters. So if you go ahead to the Python menu, you can actually filter attributes that are actually going to show up in the drop-down menu. So in this case, for something like for the ID attribute, I am using only the attribute type primitives, and for the attribute data type also only the string attributes. So that's how I filter data that's going to be fetched for this ID attribute. And for the size attribute, I go ahead and go to the, again, check for only the primitive attributes. And I have set up that minimum size is 2 for the vector 2, and the maximum size is also 2. So that means that only vector 2 attributes are going to show up in this drop-down menu. So this is a very simple way to showcase a user what kind of attributes, what kind of data is actually supported with this digital asset. After that, we also have to choose which tiles we want to copy. So for this case, I have not selected anything, so that means all the tiles that has been found are actually going to be copied. But let's say I choose my tile 0, you can see only the tile 0 is going to be copied. If I take tile 1, you see now only 2 tiles are copied. So this is a good way to kind of like only select tiles that I want to copy across the surface. So another important part is the expand border. So expand border is actually not necessary for this tutorial, but it's basically a way to kind of like extrude the sides. So for that one, it doesn't really matter. But what's cool about this is that we can actually go ahead and overlap tiles, or make them a little bit bigger. You can see if I have overlap horizontal, you can see I am using this one, and the vertical is actually a lot more useful, because you can see some of these tiles are actually cut out inside here. So that means that if I set it up 0, you can see it's actually going to be like this. So to make sure that I actually overlap them a little bit like this. So and then there's actually option for you to for the random tile placement. So that's going to be a little bit later. Let's go ahead and let's go inside this HDA and show how this is set up a little bit more. So first of all, we set up our tiles. We kind of process our tiles inside here. So this is our input of the tiles. And first thing first, we have promoted this parameter on our tiles to copy parameter. So this is where we actually get this menu that we can select which tiles we actually want to copy across. So this is a very simple way to quickly get rid of tiles that we're actually not going to use. And then one trick that is actually also very useful is actually go ahead and rename our attributes. Because these attributes, because these two attributes, tile name and tile size, are actually be used in a bunch of wrangles. And in wrangles are actually, I want to use a static name because I do not want to dynamically fetch the names of the attributes that I want to reference. What you can do is basically take the attributes and rename them with the underscore. Basically, to the static name, rename them to the static names. So that means that whatever the attribute name that user provides is going to be renamed to these two names. And then we can statically use this name inside the wrangles without worrying that this attribute is not actually present. And at the end of it, we can just go ahead and rename these attributes back to their original name, and that's it. So this is a very useful trick that you can also use to rename your attributes before the actual logic of the HDA. And after that, I want to go ahead and use a pack node, and I want to use a pack by attribute. So that means that each one of these tiles with unique names are actually going to be packed into primitive with the promoted transferred attributes of tile name and size of them. So you can see I have now, since I'm not deleting any tiles inside here, and I know that I have 3 input tiles, I have now, after the packing, I have 3 primitives with the size and names of them promoted for these packed primitives. After the packing, I want to go ahead and get my minimum sizes for the width and height for the tiles. So this is important because in the unlikely chance that I have randomized my entire tile row to be the smallest tile size, I want to make sure that I always have basically enough tiles to copy across the length of the input geometry. So basically we're going to create a kind of like a proximity grid that is only generated from the smallest width pieces of the tiles. So this is why the minimal sizes are actually important to get, and that's actually a very simple code that we run over. So we create our width and height arrays, and we just go ahead and go loop through every primitive inside here, and then we go ahead and get our size attribute. And this is where the actual attribute renaming is actually very important, because you can see I can now statically use the underscore size attribute, and I know that this attribute is actually going to be present. I do not have to like reference another attribute. I do not have to like go to the parameters of the HDA and get this style attribute name, like size attribute name, and then fetch it from that. It's actually very nice to have a setup like this with the attribute renaming. So we just get the size, and then we just check if this width size is actually already in this array, and if it is not, it's going to return like a negative value if it's not in there. And that means if the width value is not there, we can just go ahead and append it to the width and the height arrays. And the only difference between these are the x and y component of the vector 2. So the x is the width and y is actually the height. And after that, we can use the minimal function on both of these arrays and set them as a detail attribute minimum width and height. And that's basically it. And you can see we have our detail attribute minimum height and width. And then I want to actually create a size directory. And this is actually very also cool thing that we can do. It basically get all the sizes of each one of these tiles and store them into the directory. So you can see that the key for the directory is actually its unique ID, basically its ID attribute value, and the size of it is basically the vector2 value for each one of these. And it's actually also very simple to set up. Again, we create a directory, we run through every one of these primitives, and then we get our size and ID attribute values. And the only thing that we do is take our size, use our ID string as a key, and set as a size its value, and then set this directory inside here. And you can see that we can basically use this, we can reference this directory to get the size of the tile. And one thing that I also have done in this HDA, in this case, I actually have set up my error node. So this is actually very cool to have, because we want to make sure that we do not basically whenever we are working with the sizes and all of these, and we are using something like a wrangle node, there is a possibility that we actually go into the infinite loop in the cases when when the directory, when the size of some of these copied tiles are actually 0. And to make sure that none of these sizes are actually 0, we can use our report this error when the detail is basically when the minimum height or width attribute is smaller or equal 0. And I'm actually going to showcase inside here. So let me go ahead and take something like a wrangle node. Actually go ahead and use this some like a select one of these tiles and set its so that's going to be u at size equals 0. And just make sure that you are running over the primitives. So you can see that now for one of these tiles, my size is actually at 0. And it's actually going to error out this node. So you can see that in this case, it has detected that one of the tiles are actually at 0 size. And it's going to basically report this error. If you take a look at this HDA node, you can see that it's going to actually 0 height detected and 0 width detected. You basically the strings that I have set up inside here. So this is actually very useful thing also to do to set up for your digital assets. Now that our tiles are set up, we want to go ahead and create the densest possible grid from these tiles. So this includes taking the minimum values that we calculated inside this node, minimum height and width tiles, taking these values and using it inside the copy node. So you can see that at the end of it, we should have like these two, the array with the difference between all of these points are taken from the minimum values of the tile sizes. And this grid is based on the input shape that we are inputting in this roof generator. In this case, our roof is like here, and I want to make sure that since I'm going to cut out the roofs from this input shape, I want to make sure that I have covered the entire surface of this input shape. So I just have a simple grid that uses a match size, and where the scale to fit has been turned on and uniform scale has been turned off. So you can see we're just having this wraparound shape that we are using it to see how many points you have to copy across the horizontally and vertically. And this amount is basically just taking the bounding box size of the wraparound shape. In this case, we are using the z size because of the horizontal is going to be z axis, and dividing it by the minimum size of the tiles. And the minimum size are also taken from the spare input reference. That's -1. And I'm also using the ch. I'll also adding the overlap parameter because in my HDA I have ability to basically overlap tiles. So you can take a look at this. I'm like, if I start to overlap horizontal tiles, you can see that the minimum size for these tiles are actually beginning to be bigger than the actual minimum value. So this would mean that there would be space between all of the tiles, or we can make them smaller. So it means that there's actually going to be overlap on the horizontal axis. So the horizontal overlap is not really all that that uh, that necessary most of the time, because what I'm really interested is actually in vertical overlap for these tiles. You can see because of these cutouts, I want to make sure that I actually have something like this, that these tiles overlap to cover up the holes. Now that the most densest grid has been set up, I want to go ahead and transfer attributes to it, because after the copying of these points, we really don't have any attributes at all. So what I'm doing is here is transferring detail attributes from my tiles. So that would basically include only the minimum height and width, and also the size directory. And after that, I'm actually going to create a new attribute also, which is going to be called row. And the row is actually just taking its y value point, y value, and getting the first four basically characters from it. So this is going to make sure that I have actually like a kind of like a distinguishing a string value that I can use to loop over each row of geometry. So I have shown this trick before. It's basically taking the y float attribute and converting it to the string value. and this string value is going to be used as a piece attribute in the row. So this will mean that we can use this to basically iterate through each row of tiles. So we have these points, we have copied our geometry, we have transferred our attributes, we have created our piece attribute for each row, and now this is basically the most important part of this logic. We are actually using the piece from attribute from pieces node. So it requires input 1, which is just a point cloud, that this attribute is going to be basically where our tile names to the points that are going to be assigned to. And then we also need our geometry library. And our geometry library is of course our tiles. And all we have to do is go ahead and take our piece attribute. So we know that it's basically a tile name. And it's going to basically take each unique value that it has found for this attribute tile name and assign it based on this mode to these points. So you can see that it basically uses I have promoted this parameter from this node, with the exception of the more advanced like map attribute or vex expression. Since I do not need it all that complicated, I just want basic cycle, patches, noise, and random. You can see there's also a seed and there's also an offset, and some of these parameters are actually also promoted to the HDA, and you can basically take whatever parameters you want and promote to your HDA on how intricate you want to get for these points. Now that we have assigned our IDs based on the mode, we want to go ahead and create a new grid that's going to respect the sizes of each one of these tiles. So if I go ahead and start copying this geometry across this most densest grid, you can see that our geometries actually would overlap each other whenever the tile size is actually bigger than the minimal size of the tiles. So you can see that where the tile is actually the smallest one, you can see the copying is actually correct because of the size actually correctly set up. But for the bigger tiles, since the most densest grid is not respecting its size, we have to go ahead and create a new grid that's going to respect the size of each one of these tiles. So let's go ahead and do that. Let me delete these copy to points. So this is done for each row of the roof. So in this case, I'm using the piece attribute row. Let's take a look at it. Let's just go through each one of these. You can see when we copy, we have correct amount of space between each tile. So this is where the make pattern wrangle comes in handy. So let me go through this. So first of all, we are running over the details, so only one time, and we have no input 0 because this node is actually going to create a new point. So we want to make sure that we start with no geometry, and we just have to go ahead and reference attributes from the input 1 and 2. So let's take a look at it. So first of all, we get our size dictionary. So the size dictionaries come from here where we actually transfer our attributes. We get our size dictionary. Then we get our bounding box, and the bounding box comes from input 2, and the bounding box is actually the most densest grid size. So this is important because it's not necessarily we do not need it 100% needed, but it is a good idea to basically not to write too many points for each one of these rows because since this is the most densest grid, so this is the most dense points that are ever going to be in this pattern. So that means that most likely, since we are randomizing our tiles, we are going to get some bigger tiles. So that means that the bigger tiles are actually going to make this the number of points that we need to fill each row a smaller amount. So that means if we have exceeded the bounding box size of the z of this geometry, that means that we have filled this row. That means we do not have to generate more points for each one of these rows. So this is why I'm actually fetching the bounding box size also. And then I have also the float parameter of the written size. So written size is basically we're going to increment this value for each one of these points that we are iterating over. So let's take a look at it. So first of all, since we are inputting these points, and in these points are also basically we are looping over each one of these points, and we are fetching its values. So for each one of these points, and then we check if we have not exceeded our bounding box size of the of our most densest grid. And if we have not, we check the point position of the point that we are looping over. We are taking the ID attribute, the tile name, and its size. And the size is actually fetched from the dictionary. So you see that in the size we're using the ID value as a key to fetch that tile size. And after that, what you can do is create a new point. And the reason why we're getting the position attribute, this is want to make sure that the Y position is actually correct. So this is why I'm using the p.y value, so that the height of this row is actually correct for each one of these rows. And then I just want to go ahead and set it as a written size, as a z position. And after that, I want to set for my new points also its tile name, and the tile name is going to be the ID. And then I want to go ahead and basically update my written size, so that for the next iteration, the written size is going to start at the end of the previous point. So that means that our points are actually going to move forward. And that's basically it. And also I'm adding the overlap H option that's going to overlap them in the horizontally. And that's basically it for this kind of a pattern. So you can see that in this case, we have this kind of a grid, which is not uniform anymore. Let's take a look at this. It's right here. And then all we have to do is go ahead and copy the points here. You see, now we have our tiles. After it has been copied, I just want to go ahead and apply for each one of these primitive its own unique ID. So this can be used outside of the HDA to maybe like offset UVs for each one of these tiles. Then I'm using a match size node to basically make sure that when I'm starting to Boolean it out, I have basically overlapped my input tile over it. And then I'm just going to go ahead and use the Boolean node. You can see I have Boolean out this shape. It's very simple. We unpack our geometry. We use our connectivity. So the connectivity node is used to be able to use the compile block to actually make this Boolean a lot faster. So we are basically Boolean out each one of these tiles separately, but since this is a compile block, we can use a multi-threaded workflow to actually cut it out a lot faster than we would do it on a single thread without the compile block. And we just go ahead and Boolean out like that. And after the Boolean, we just do some transforming back to its original place. And this is how our roof tile is going to be created. And then after that, we can use it, we can transform it again. You can see like that. So this is a basic workflow how it is done. So you can basically add a bunch of other things, a bunch of other options. For me, I actually really like the ability to give it an offset for the odd row. So the way that this is set up is actually also very simple. If I have selected in my parameters offset odd row, I run this wrangle. And this wrangle is actually very simple. I check the iteration and I check the minimum width value of the tile. And then basically, if this is an odd row, I taking the half of the minimum width of the minimum width of the tile, and I just offset all my points by that amount. So this basically creates this cool effect, which is very noticeable when you want to just copy one tile. So let's say I want to copy this tile, and if I have turn off offset odd rows, you can see this doesn't look all that great because they are all following in the same row. But if I go ahead and use an offset odd rows, you can see this is more like a typical roof would look like. So that is actually a very cool thing to have also. And one last thing that I wanted to showcase is actually randomization between different tiles. So in this case, you will see that it's very easily seen that basically the randomization is actually same between all of these primitives, and that is because of these noises that is being used is basically position based, and since all of our primitives when we are actually moving it to its flat position, they're basically going to sample from the same points from the same space in the world space. So this is where we want to go ahead and apply our seed, which is basically we want to differentiate our seed for each one of these loops. So this is where the piece attribute comes in handy. So what I have here is actually I have go ahead and set up integer piece attribute, which is going to take the primitive attribute, primitive value multiplied by 10. So what's uh, what's great about this is that we have basically for each one of these primitives, there's a big difference between all of these points values, and we're going to use this value for the randomization seed. So let's go inside here, and what I have here is I'm referencing my input geometry that has this piece attribute, and I have actually go ahead and created this expression already. So I'm taking the seed attribute from my parameters, which is a seed parameter, and then I'm plus the primitive value of the basically primitive uh, attribute value from my seed attribute parameter inside here. So inside here I have my only one piece attribute that I can select. It's basically going to take the value from here, and in this case, since in this loop that I'm looping over, the piece attribute is 110, and I'm using the seed attribute is 3, so that means 110 plus 3, my seed is 103, and this is going to make sure that for each loop our piece attribute is going to be different for my geometry, and it's going to make sure that the randomization is going to be different. And if you take a look at it, you can see that right now for each one of these primitives the tiles are actually different. Right, and if you go ahead and disable this one, this should basically make sure that it is the same for across all of them. So it can be basically turned on or off if you have if you have your seed attribute. So this is everything that I wanted to cover in this video. I hope you learned something, and see you next time.